Hi, and welcome to the next video in the Combinatorics series. This time we'll be talking about just the basic idea of this principle of counting in two ways. Now, the idea here is that if you can take a set and enumerate its elements using one counting method and then another counting method, then if each of these counting methods gives you a formula for the number of elements in the set, then these two formulas must be equal to each other in the sense that for the same input, each formula takes the same value. We can use this to basically establish some identities. The textbook gives a nice and brief sort of philosophical meditation on this idea. I'll just sort of chime in and say, not only do I agree, of course, with what was in the textbook on this point, but also I think this is more pervasive, really, right? I mean, we don't even have to be talking about combinatorics. In general, in all of mathematics, whenever we state an interesting equality, then we have something on the left which is not obviously the same thing on the right. I mean, you could state an uninteresting equality like x equals x or something, but as long as you have something on the left, which is apparently not the same thing as what's on the right, then you must be talking about a single object presented in two different ways. And then you recover some information out of the fact that a single object is presented in two different ways. But anyway, so to give an example of counting in two different ways, let's consider that you have a set of n elements. Now, here I'm demonstrating on a set of 4 elements, but the more general case is that we'll have a set of n elements. And we would like to find all ways of choosing 2-element subsets. In this particular small example, I've enumerated all of them. So just by brute force, we can see that there are 6 of them in this case. Now let's try to count this set, both in the, this particular case, but also thinking about how it generalizes to the more general case in 2 different ways. The first way is to, in fact, look at all ordered pairs, right? So if we're taking 2-element subsets and sets are necessarily unordered, then we would not count the set 1, 2 as distinct from 2, 1. But we could count with order anyway and see that every set corresponds to 2 ordered pairs, right? So the set 1, 2 corresponds to the pair 1, 2 as well as the pair 2, 1, right? And so on, right? That every set of 2 elements corresponds to 2 ordered pairs of those same 2 elements, so that the number of ordered pairs is twice as big as the number of sets. And therefore, if we count up the ordered pairs and divide by 2, we'll have the count for the number of 2-element sets. So, how many ordered pairs are there? The grid here makes it clear that there are 4 times 3. Or, you could use your permutation formula and say that we're taking 4 elements taken 2 at a time. So again, 4 times 3, however you like to think about that. But in the more general case, the count will always be n minus 1. And so we take that divided by 2. And that is our first way of counting this set, right? So for an n-element set, the number of 2-element subsets is given by this formula, n minus 1 over 2. Now let's count the same set in a different way. So to proceed methodically, let's imagine that we take some element like, for instance, 4, and let's look for all 2-element subsets containing 4 and any number bigger than 4. But since there aren't any, then this just corresponds to no elements at all. Now let's do it again, but this time let's start with 3, and again we'll look for all of the 2-element subsets containing 3 and any number greater than 3. This corresponds to just one 2-element subset, which is 3, 4. Let's do it again. Let's pick 2 and look for all 2-element subsets with 2 and greater. That gets us 2, 3, and 2, 4. If we picked 1, then we'd get 1, 2, 1, 3, 1, 4. and there's nothing else, right? I've exhausted all possibilities, having considered taking each possible element and only the elements greater than it. This effectively gets us a count of 0 plus 1 plus 2 plus 3, or more generally, right, for the case of an n-element subset, then the formula that we found for counting the set is the sum from 0 to n minus 1 on the index I. And because these are two ways of counting the same set, then they must be, right, the two formulas must give us the same value. And that is the principle of counting in two ways.